Okay, so this, the reason I'm again doing this video for you, I'll post it on YouTube and then post the YouTube link in your Moodle page, is because I've never seen the 6-step process anywhere else on how to take the mass spec data and turn it into the molecular formula. So it pulls together the nitrogen rule, the hydrogen rule, the rule of 13, lots of the different guidelines that you can see videos about each one in particular. I put it together in a 6-step process based on what I learned in graduate school and my attempt to make it as smooth as possible for students as well. Okay, so this is the last slide deck that shows using the given mass spectrometry data to determine the molecular formula. And let me just make the table here. So the M plus 1, the M plus 2, and this is the mass to charge ratio data, and then the relative intensity. I'm just remaking the table that is your second to last slide. It's the one right before your wrap up, okay, in that mass spec slide set. So what it tells you is that M for this example is 59, M plus 1, of course, then is 60, and M plus 2 is 61. So the relative intensity of the M peak is 100%. So it's both the parent and the base peak, which doesn't happen all the time. The 3.85% is the relative intensity of the M plus 1 peak, and 0.0127% is the relative intensity of the M plus 2 peak. So this table is literally all you need to determine the molecular formula. And let me show you how. Okay, so step 1 in my 6-step process is to check that the relative intensity of the base peak is 100%. If your base peak is not listed as 100%, you need to rescale, because that's what a base peak is supposed to be. Step 2 is to apply the nitrogen rule, okay? So if M is odd, there must be an odd number of nitrogens. Okay, step 3, I thought there were 2 participants, weird, is to use the relative intensity of the M plus 1 peak to find the number of carbon atoms, okay? Okay, so in this case, M plus 1 relative intensity divided by the abundance of carbon-13 in nature, which is 1.1%, gives us 3.85 right here. See, that's where the 3.85 comes from. 1.1 is the natural abundance of carbon-13. So we're using this isotope of carbon to determine how many carbon atoms there are. So that equals 3.5. So that means there are 3 or 4 carbons in our molecule. The rule on this is we want to round up if greater than 0.7. We round down if less than 0.4. But this is exactly 0.5. So we're going to have to see how things go. Okay, so just stick a pin in it for right now that it's either 3 or 4 carbons. And then we're on step 4. You look at the M+2 peak to see if there's evidence of bromine, chlorine, or sulfur. Okay. Okay, so if I had bromine, what would be the relative intensity relationship between M and M+2? They'd be 50-50, like the same intensity. Very good. What if it was a chlorine? What would be the proportion? 3-to-1. And if it's sulfur, it would be about 4%. Okay, but 0.0127 is a whole lot less than 4%. So there's no, in other words, there's no evidence of bromine, chlorine, or sulfur. Okay, in this case, because we don't see a 1-to-1 ratio, we don't see a 3-to-1 ratio, and we don't see a 96-to-4 ratio. So none of them are there. For the good of the cause, I'll go ahead and write 1-to-1 ratio for bromine, 3-to-1 ratio for chlorine, or 96-to-4 ratio for sulfur. We don't see that between M and M+2 this time. So that brings us to step 5. So we're going to subtract the isotopic masses of the known atoms from the mass of the entire compound to see how many atomic mass units are left for oxygen, hydrogen, additional nitrogens, and so on, okay? So the mass to charge ratio of our M peak minus, let's try 3 carbon atoms and a nitrogen. So the mass to charge ratio of our parent, our M, which is also in this case our base peak, is 59. We're going to subtract 3 times 12 because we're going to brainstorm using 3 carbons before we try 4 carbons, okay? And we're going to subtract 1 nitrogen, which is 14, because remember the M peak was an odd number, so we have an odd number of nitrogens. So we either have 1 nitrogen or 3 nitrogens or 5 nitrogens. It's an odd number of nitrogens. Given the mass of the parent is only 59, let's subtract 1 nitrogen and see where we are. So that gives us 9 atomic mass units left for other things like oxygen, 16, hydrogen, 2 more nitrogens. Okay. Yes, sure. So we have 9 atomic mass units left for any oxygens, halogens other than bromine or chlorine, 2 more nitrogens, so we'd still have an odd number of nitrogens. It seems like the most logical is to conclude that those 9 atomic mass units are hydrogens. Do you see that? Because oxygen has a mass of 16, 2 more nitrogens would have a mass of 28. It seems like those 9 atomic mass units must be hydrogens. Do you see the logic of that? Okay. Yes, I just put a smiley face. Okay. So step 6, is to evaluate the possibilities of the molecular formula. So I know we have 3 carbon atoms, not 4, because how much does a carbon atom have for its mass? 12, right? We only have 9 atomic mass units. So we absolutely know we have 3 carbon atoms, not 4. So that was a good estimation earlier. And we have 1 nitrogen atom. We don't have 3 or 5 or some other odd number because we don't have enough atomic mass for that. But we do know it's a good estimation that we have 9 hydrogens. So that is our molecular formula of the compound based on the table of data that were given in the beginning. Does that make sense? Okay. I bet you'd like to do another example, right? Okay. So let's do another example. Everyone all set here? No, not yet. Let me pass these out. Hold on. So let's do another example together. And again, this data came from the last slide in the slide set that was already posted on Moodle. So this one, we'll walk through this one together. Sometimes instead of giving you just a data table, you'll be given the spectrum. So I wanted you to get a feel for what that is like, seeing the spectrum yourself and maybe even creating a data table. I went ahead and created the data table for you in this example though. So we're going to determine the molecular formula of the compound and using the same 6-step process, okay? So step 1 is check that the relative intensity of the base peak is 100%. It is. You can see the base peak is 100%, so we don't need to rescale our spectrum, okay? So our step 2 is to apply the nitrogen rule. So what is our parent? So you can see the largest peak over here is our parent, right here. There is our parent. There is our M, okay? And it has a mass to charge ratio of 102, as it's written in the table. If you were to use a ruler, you would notice that it has a relative intensity of 20.7%. The M+1 peak right here, this little guy, is a mass to charge ratio of 103. It has a 5.5% relative intensity. And then this M+2 is a mass to charge ratio of 104, and it has a relative intensity of 6.7. So you could have determined the information in this table yourself just using a ruler, but I went ahead and did it for you in this case. So step 2, applying the nitrogen rule, you notice that the M peak is even. So that tells us that we have an even number of nitrogens or 0 nitrogens, okay? Okay. Step 3 is to use the relative intensity of the M+1 peak to determine the number of carbon atoms. So step 3, we have our M+1 intensity divided by the natural abundance of carbon-13, which is 1.1%. So M+1 is 5.5%. The relative abundance of carbon-13 is 1.1%. So that tells us that we have 5 carbon atoms. And then in step 4, I'm going to come over here. This is where we use the relative intensity of M+2 compared to M to look for evidence of bromine, chlorine, or sulfur. Okay, so okay, so if you have chlorine, you would have a 3-to-1 ratio of the M to the M+1. If you had bromine, you would have a 1-to-1 ratio of the relative intensity of the M and M+2. And if you have sulfur, you would have a 96-to-4 ratio of the M to the M+2. Remember, this is 3-to-1, this is 1-to-1, this is 96-to-4. When you look at M and M+2, what do we notice? So we have 20.7 divided by 6.7, and that equals a 3-to-1 ratio. So there's chlorine. Therefore, there's a chlorine present. Okay? So step 5, you subtract the isotopic masses of the known atoms from the parent. So our parent was 102. We're going to subtract 5 carbon atoms, and we're going to subtract, let's subtract 0. So this is our parent. This is number of carbon. Let's assume that because we have an even number and chlorine's fairly heavy, that we have 0 nitrogens instead of 2 of them. Okay. And then subtract 35 for the chlorine, and that gives us 7 hydrogens possible. Do you see how we couldn't have minus 28 right here? We would have gotten a negative number. That's why I know that there's 0 nitrogens and not 2 or 4 or 6. Yes. You're welcome. Okay, so that tells us that when we put all that together, our step 6, to pull it all together, it means that we have a molecular formula of C5H7Cl. Okay? Isn't that fun? Yeah, it's not bad. This mass spec is actually from the compound one chloro, 1-cyclopentene. So I obtained the spectrum from the NIST Chem webbook website to give as an example for you. Okay. Are you ready for another example? All right. So the fun part about the next example is that you're going to use 2 kinds of spectral data to put this together. And this is the kind of exercise that you'll do on your test as well. So I'm going to enjoy this detective work. You want to like stretch out your fingers and let's get going here. So I was super nice, gave you the relative intensities of the M and the M+1 peak. There's there's no M+2 peak that's discernible in this spectrum. There's just the M and the M+1. So our first step, we're going to check that the base peak is 100%, and it is. You can see the base peak here is also, in this case, the M, just like we've seen before. So that is all set. We don't need to rescale the spectrum. Step 2, what do we do for step 2? We apply the nitrogen rule. If we have an even number, then we have either an even number of nitrogens or 0 nitrogens. This is an odd number for the M. So what does that tell us? We have an odd number of nitrogens, okay? So given this mass, I would propose that we start with 1 nitrogen, not 3 or 5 or 7, okay? So let's assume there's 1 nitrogen. And then step 3 is to determine how many carbon atoms we have. So we have our M+1 intensity divided by the natural abundance of carbon-13. So we get 8.7% divided by 1.1%. And that comes out to basically 8. So 8 carbon atoms. Yes. Do you notice that they're to the left? So they're fragments. The biggest peak, the furthest to the right. Yep. Good question. So in step 4, we look at the M+2 peak to see if there's evidence of bromine, chlorine, or sulfur. We don't even see an M+2 peak. So we don't have them. So that leads us to step 5. That's where we subtract the isotopic masses of the known atoms from the parent. So we have a parent of 117. We're going to subtract 8 times 12 for the carbons. We're going to subtract 14 for 1 nitrogen, and we get a 7. Okay, 7 atomic mass units is left for 2 more nitrogens, an oxygen atom, or hydrogens. What do you think the 7 atomic mass units are? Hydrogens. Okay, so that gives us a molecular formula of C8H7N. Okay, now this problem is not just determine what the molecular formula is, but what's a plausible structure. Okay, so that's why the IR is here as well. So when we were determining plausible structures in class, the next thing we did, and this will be our step 7 for a problem like this where we're trying to determine not just the molecular formula, but also plausible structures, we want to know how many degrees of unsaturation are there, or double bond equivalents. Okay, so I'm introducing a step 7 here because this is a larger type of problem where we determine plausible structures. So we're going to determine degrees of unsaturation. So that formula, remember, is carbon minus half of the hydrogens plus half of the nitrogens plus 1 minus half of any halogens. So in this case, we're going to have 8 carbons minus 7 halves because of the hydrogens plus 1 half because of the number of nitrogens plus 1 minus 0. So that gives us 6. Okay, so how many ways can we have a degree of unsaturation of 6? We can have 6 double bonds. We could have 6 pi bonds. We could have 5 pi bonds in a ring, 4 pi bonds in 2 rings, and so on and so forth. Okay, but in some way, we have 6 degrees of unsaturation. That's some combination of pi bonds and rings. Okay, now the next step, or step 8 for a case like this, is what do we see in the IR? Because that will help us determine what these 6 degrees of unsaturation are caused by. So in the IR spectrum, what do we see? We see a couple different things, don't we? Can you name one that you see that's really helpful? You bet. I see either a carbon-carbon triple bond or a carbon-nitrogen triple bond. But in any case, there's definitely an alkyne in here. Okay. Another thing I see monosubstituted aromatic ring pattern of Fermi resonance bands. What's that? There's a benzene ring in this guy. Yes, absolutely. And what else do I see? I see evidence of, in this region here, I see evidence of sp2 hybridized carbon to hydrogen stretches. I see a little tiny one here of sp3 carbon to hydrogen stretches. And this and this are from different modes of carbon-carbon double bond stretches. Remember, because there are different kinds of modes of stretching. So when I put that all together, one proposed structure that I would have is this one, where I have an aromatic ring with an R group coming off it. That's what this pattern of Fermi resonance bands tells me. I also see that I have some kind of alkyne. It looks like only one. It's a very small proportion of the molecule. That's an sp3 carbon to hydrogen stretch. But I do see lots of sp2 carbon hydrogen stretches. And I see evidence of carbon-carbon double bond stretches. That's consistent with this information and this information. Okay, so this is actually really the structure of the molecule as well. This is benzyl nitrile. That's what the mass spec and the IR are from, benzyl nitrile. Do you see how all the evidence came together to demonstrate that? Okay.